Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 27, 2026, just 3 days ago. It introduces a novel framework for spatial awareness and image generation, achieving a pairwise accuracy of nearly 96% and boosting in-domain spatial scores from roughly 2.2 up to 7.8. The paper is titled, Enhancing Spatial Understanding and Image Generation via Reward Modeling. And as we'll see later, the way this method uses reinforcement learning to fix complex spatial errors is really quite impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Alright, Figure 1 highlights the core problem this paper addresses, the failure of current metrics to judge spatial correctness. It shows a prompt asking for specific positioning, like a laptop slightly left of center and a coffee cup to its right. The image on the left, labeled Error Relationships, clearly gets this wrong, because it places the cup on the left. Surprisingly, standard reward models like HPS version 3 and Image Reward assign higher scores to this incorrect image, effectively preferring the mistake. In contrast, the image on the right achieves true spatial alignment, yet those same models give it lower scores. Finally, the bottom row shows that the author's new spatial score correctly flips this, assigning a much higher value to the accurate image. Next, Figure 2 examines rule-based metrics like general eval, which depend on standard object detectors. Panel A shows this method struggling with long prompts that contain intricate spatial relationships. Then, Panel B reveals a flaw where detectors misinterpret occlusions. In the banana example, the detector incorrectly counts only one item due to overlap, whereas a vision language model sees both. This proves detection-based rewards are often too brittle for complex spatial training. Well, to fix those evaluation issues, Figure 3 outlines the creation of the SpatialReward-Dataset. Panel B details the core pipeline. The authors take a complex perfect prompt and use GPT-5 to generate a perturbed prompt by flipping specific spatial terms, like changing left to right. They then generate images for both versions and filter them with human experts, creating adversarial pairs where the model must distinguish between a correct layout and a subtle spatial error. Meanwhile, Panel A illustrates the wide range of scenarios, like kitchens and living rooms, and the bottom charts confirm that these prompts are dense with spatial relations, ensuring the model tackles real complexity. So, with the dataset established, Figure 4 now maps out the training pipeline used to actually improve the model. On the left, the policy model receives a complex prompt and generates a batch of candidate images, which are immediately rated by the spatial score model. The middle section introduces a key innovation. Instead of using every sample, the system ranks them and applies a top K and bottom K filtering strategy. This selects only the most accurate and least accurate images to calculate the learning signal. Finally, on the right, these filtered samples drive the policy gradient optimization, which updates the model to reinforce correct spatial layouts while penalizing specific layout errors. Okay, having defined the training process, Table 1 presents the pairwise accuracy of the spatial score reward model itself compared to various baselines. First, looking at the image reward models on the left, standard metrics like PIC-score and HPS version 3 struggle significantly, with scores hovering between 48 and 65%. Moving right, the open-source QN 2.5 VL series improves with scale, but still caps out around 76%. Finally, the last two columns reveal the most striking result. Spatial score achieves an overall accuracy of nearly 96%. This surpasses even the massive proprietary models like Gemini 2.5 Pro, demonstrating that a specialized model can beat general-purpose giants on spatial reasoning. Alright, we just saw that the reward model is accurate. Now, Table 2 asks if using it actually makes the generated images better. It compares the base Flux 1 dev model against a baseline, using general eval and the author's approach. Starting with the spatial score column on the left, the base model begins at 2.18. The author's method dramatically boosts this to 7.81, confirming that the reinforcement learning successfully optimized the target. Crucially, this success translates to external benchmarks like DPG bench and TIIF bench in the center columns. While the baseline flow GRPO sometimes degrades performance, dropping the DPG score to 0.74, the new model consistently achieves the highest values across the board. Wrapping up, two takeaways stand out. First, standard aesthetic rewards fail at complex spatial logic. Second, by training a specialized reward model and applying reinforcement learning, we can force generative models to accurately respect layout. This suggests that better feedback signals, rather than just larger models, are key to precise control. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.